right, hello everyone. We'll start shortly. As usual, please write down your name on the chat as we later will count it as attendance. We'll pick it up where we left last time. We were working on calculating the arc length of a particular curve. So let me pick it up from there. The curve we were talking about was an asteroid, and I'll show it to you in just a moment. I actually, so let's see, we were working with this one over here last time. And let me just remind you what this curve was. We were actually doing, I didn't specify last time, but we were doing the one with a equals 1, right? So the a was a parameter there, and it had to be 1 for the ones we were doing. So here's a picture of how this asteroid is drawn as a parametric equation that I did in Mathematica. Let me show it to you. So we had done that one before. So here's a description of this asteroid. So as you range from 0 to 2 pi, so right here is what happens from 0 to pi over 2. Then here's pi, 3 pi over 2, and last it draws this last part, and it looks like this. And that's a curve we're referring to as an asteroid. Okay, and what we were talking about is figuring out the arc length of that curve. So here we go. This is what we had done last time. The formula for the arc length is the derivative square of the x function with respect to t, this one over here, the derivative of the y function with respect to t of this one over here, and we carried it all over here, and we substituted the derivatives here, we squared them, we factored out what we could, and then we had a sine square plus cosine square equals 1 right there, a little bit further back, and then we cancel the square root with the square and put absolute value bars here. And remember, we had said that we were doing a equals 1. So that takes care of this one over here. And the other thing to note, that as you saw from the graph that I just showed you, our graph was symmetric, right? So we had 4 pieces that were exactly the same. So instead of maybe doing from 0 to 2 pi, maybe we do from 0 to pi over 2, and we multiply by 4. So that's how we're going to continue right here. This is 3 times, and then we're going to multiply by 4 because we're going to use the symmetry. And now will be from 0 to pi over 2 sine t cosine t dt. And this is by symmetry. All right. And this is also good for us to do the integral because between 0 and pi over 2, both sine and cosine are positive. So both are positive. So we don't need the absolute value. So this becomes this integral over here, sine t times cosine t, which is easy to integrate, right? Because the derivative of sine is cosine. So you can simply do a u substitution if you wanted to, or in this case, we can even write down what the answer is, right? This is simply sine squared t over 2, right? Because when you take the derivative of this, you get the 2 comes down, cancels with this 2, you get sine t times the derivative of sine t, which is cosine t, right? So we do this from 0 to pi over 2. And this becomes 12 sine square of pi over 2 over 2 minus sine square of 0 over 2. This is 1, the sine square, and this is 0. So we get 12 times 1/2, which is 6. So the arc length of that curve is actually 6. All right? And that finishes up our example. We'll actually we'll talk a little bit more about arc length of curves when we get into the next couple of sections. And I want to get started on that. So the next section is 12.2, and it's called polar coordinates. Polar coordinates. Okay, and this is a new way of locating points in the Cartesian plane, in the plane, right? Usually the way we find out where points are located is by providing their x coordinate and their y coordinate. We call these the rectangular coordinates or Cartesian coordinates in honor of René Descartes. Okay, and you know how this is done. You essentially look for a particular point. You need to identify its x coordinate and its y coordinate. So the right way of thinking about this is that there is a grid here like this, right? So we use a square grid to locate where points are. You need to tell me their x coordinate and their y coordinate, and I know where they are. That's our regular system of coordinates. Now, that's the regular one. Now here's the new one. So new system. And the way I would like you to think of it is as a radar or a sonar, right? So if you've ever seen how those work, they sort of scan in a radial way, so they go all around, and they then identify where you hit an object, and you can tell how far they are. So the two questions that the new system asks about a particular location of a point is how far and in which direction. All right, and so the way to think about it is as follows. So this time around, how far means from a given center, which we call the origin. How far would tell you at which of these circles you would find it, right? And in which direction would tell you in which of these rays. Okay, so this is the main difference. Here we locate points. You tell me, for example, 3 units and 90 degrees. So 3 units pi over 2. So I go, imagine that each one of these is 1. So 1, 2, 3, and then pi over 2 would be here, right? So the coordinates of this guy will be 3 pi over 2, right? So in general, we have 2 coordinates, r and theta. The r tells you how far it is from the center. Distance to the center. And the theta tells you the angle with the horizontal axis. Right? This one that I colored in green, well, you can barely appreciate the color. Let me put it purple over here. That's the one we measure the direction with. All right. So is that clear? Every point has two coordinates now, but it's not going to be the x and the y. It's going to be the radius, r, and the theta, the angle, right? A radius and an angle. All right. So let's put it in practice. Let's do example 1. And well, actually, a word of, well, maybe we first do the example and then I'll give you a few observations, some things to keep in mind. So let's start with this example 1. It says the following. It says, graph the following points in polar coordinates. Graph the following. We have the point Q, 1,5 pi over 4. The point R, -1, 2 pi over 7 pi over 4. And the point S, which is 2, -3 pi over 2. Okay? All right, so let's do it. First, like we said, we need an idea of where our x-axis is, our horizontal axis, and our origin. So here it is. So to do the point 1,5 pi over 4, we go 1 here. So it's gonna be on this circle. Okay. And now we have an angle of 5 pi over 4, right? So that's an angle of pi, that's 180 degrees, and then pi over 4 more. So that's 45 degrees more, right? So it will be right here. This is an angle of 5 pi over 4. So right where this direction and this circle cross, that's where your point is. This is the point Q. Okay? Is that clear? All right. Now, notice the next one. The next one is kind of weird because it says radius -1. All right? So what is the meaning of radius -1? Well, when the radius has a negative sign, what you're supposed to do is to take the radius 1, but go in the opposite direction. All right? So this one has radius -1. So we should actually start in the opposite direction right here, right? And then an angle of 7 pi over 4, right? Or you could do it, you can always do, you know, like if it was a positive one and then switch directions, all right? So 7 pi over 4, it goes like this. So this is 5 pi over 4, 6 pi over 4 will be right here. And then 7 pi over 4 is right here. So let me mark it here. This is the angle, 7 pi over 4. Right? So had this been a 1, if this had been 1, 7 pi over 4, the answer would be this one. But because it is -1, we go in the opposite direction. So we need to go in the opposite direction. And we have this one. This is the point R. -1, 7 pi over 4. Okay, it's this one over here. All right, last. 2, -3 pi over 2. So 2, now we go here. So now we're working with this bigger circle. And the angle is -3 pi over 2, right? So now we go in the negative direction. And we go pi over 2, pi, 3 pi over 2, right? So it will be this angle. -3 pi over 2 is this angle. So our point is going to be this one. Okay, all right. Now, I hope you realize with this one over here, you come to appreciate one important aspect of polar equations. See, with rectangular equations, with the ones we usually use, every point has one name only, one set of coordinates. There's only one x and there's only one y. See, with polar coordinates, that's not the case. There's many possibilities. Why? Because we can specify the radius positive and then go around many times with the angle, right? And stop when we want. Or we can even go to, we can have a negative radius and stop where there is the opposite angle, okay? So I'll make a note of that and show you some examples of how that can happen. So we can write down different coordinates for the same point, okay? And that could be a good thing and that could be a bad thing. It's a bad thing in the sense that it makes it more complicated to ascertain when a given equation has a specific point in it or not. But it gives us also more flexibility, and we can come up with graphs that are more rich in a certain sense. All right, so let me go back to the page and I'll show you what I mean when I say all of these. So we can, I can show you different ways of writing the same point. Okay, so remark. In polar coordinates, the same point may have different coordinates. All right, and as an example, I'm gonna talk to you about this one over here. So I'll make it super simple. Let's talk about this point where this is radius, say 2. So this distance is 2. And we go at 45 degrees, pi over 4. All right, so what are the polar coordinates of this point? Well, it could be radius 2 and angle pi over 4, right? That's the canonical one, like the easiest one. Yeah, but just as I was telling you, that's one of them. But what if instead of stopping at pi over 4, we go once around? So we go, instead of this angle pi over 4, we go like this. And that's allowed, right? That's pi over 4 plus 2 pi. So that's also the same point. Is also the same point with coordinates where we add 2 pi. So that would be 9 pi over 4. Right? And guess what? There is no reason why we should stop at once around. We can go 2 times around. So this is also the same as the point with coordinates 2, and then go another 2 pi over here. So it would be 2 times 4 is 8 plus 9, that's 17 pi over 4. And more, right? And I can keep going. Hey, I can also go the other way around. Yes, I can also go with respect to going in the opposite direction. So this is also the same as if I go right, now I go in the negative way. And in the negative way, this is going to be negative 7 pi over 4. And I can go more on that side as well. So this is also negative 15 pi over 4, etc. Right? Now that's not the only difficulty. I can also use a negative radius. So I can write it as negative 2, and what angle? Someone tell me, which angle could I put here so that it is the same point? Daniel says 5 pi over 4. Well, let's check it out. So it would need to be this one over here, right? It would need to be here. So it should be from here to here. That's right. That's 5 pi over 4. And then because it's negative, you go here. Very good. So 5 pi over 4. Right? And then you can also add more terms. It doesn't need to be 5 pi over 4. It could be 5 pi over 4 plus an additional term. So it could also be negative 2 and then 5 pi over 4 plus 2 pi. That would be plus 8. So that's 13 pi over 4. And more terms or going in the negative direction as well. So it could also be instead of 5 pi over 4 coming this way, I could go the other way, which is negative 3 pi over 4. You see, all of these are different polar coordinates of the same point. Okay, be aware of that. This is really important that we don't have the unique set of polar coordinates in here. All right. So then, okay, so we have a new system, a new way in which we can write points, right? It's like, you know English, and then I'm showing you that there's another language, say Spanish, and then the first thing you're gonna ask yourselves is, well, how do we go from one to the other? How do we translate English to Spanish or Spanish to English, right? What's the dictionary? How can we connect one to the other? So that's our next topic here, how to converting between polar and rectangular coordinates. All right, how do we do it? Well, it's actually not that hard. All right, so let me show you what is the main idea. See, the main idea is that when you have a point with regular coordinates x, comma, y, these are rectangular, what you know is that this is x and this is y, right? And with the appropriate signs. I mean, I know I chose a point in the first quadrant, and things could be harder if I choose a different a point in a different quadrant, but it's just to give you an idea of how it works. So in polar coordinates, from here to here would be the radius. So this would be the radius. And this would be the angle, right? At least one way of writing it. I mean, we know we can go more turns, but this would be one possibility, right? And if we consider these two, how can we relate all of these quantities? Well, to begin with, we can relate x, y, and r with the Pythagorean theorem, right? And what it says is that x squared plus y squared equals r squared, all right? So look, this is an easy way to get r if you know x and y, right? To get r, you simply plug your x and your y, you square them, and then take the square root, right? So in other words, if you want to get the r, what you do is you get x squared plus y squared, and then you take the square root. Now, we can also get from here the angle. See, how can we relate this theta with y and x? What would be a function that relates those two? Theta to this x and y. That's correct. Daniel, again, good. Tangent, right? Tangent of an angle is opposite over adjacent. So we also know that tangent of theta is y over x. So that's another way, that's a way we can get the theta. To get the theta, we calculate y over x and then do inverse tangent. But be careful because inverse tangent only has as domain from negative pi over 2 to pi over 2. So if you are between here and here, between in the fourth or in the second quadrant, in the first, I mean, fourth or first, you're good. But if you're here, you need to figure out the inverse tangent and then add pi so that you're located in the right way. All right? So I'm gonna put here, use inverse tangent if needed, with caution when in second or third quadrant. We'll explain more when we get to the specific exercises. All right, but that answers the question of how we get the polar coordinates from the rectangular coordinates, right? You have the x and the y, you plug them here, you get the r, you plug them here, you get tangent of theta, and then to figure out theta, you do inverse tangent. Depending on which quadrant you are, you may need to add pi or not. Now, the other way around is actually easier. So this answers the question. So to summarize, so from rectangular to polar, this is a summary of what we just explained. The r is x squared plus y squared, and the tangent of theta is y over x. So that's one. How about the other way around, from polar to rectangular? Well, that's also easy, and all we need to realize are the other trigonometric functions that apply to this triangle over here, namely sine and cosine, right? So if you know theta and r, how can you relate theta r and x, or theta r and y? And the answers to those questions are sine and cosine. So we know that sine of theta, right here, sine of theta would be the opposite over the hypotenuse. So y over r. And we know that cosine of theta is the adjacent over the hypotenuse. So that's x over r. And then if you solve for x and y, you get that x is r cosine theta and y is r sine theta. So there you have it. These are your formulas to go from one. So these are from rectangular to polar, and these are from polar to rectangular, right? Is that clear? Let's put them in practice with a specific example. Let's do example 2. Example 2 says, express the point with polar coordinates 2, 3 pi over 4 in Cartesian. From polar to Cartesian. Remember, Cartesian and rectangular, those are just words that mean the same thing. All right? So we want to go from polar to Cartesian. So we actually need these over here, these two over here. Okay? So here, what is the r? Well, this is the first coordinate, right? It's always the first coordinate. The r is 2, and the theta is 3 pi over 4. So we use these ones over here. So x and y are supposed to be r cosine theta and r sine theta. And this one will be 2 cosine of 3 pi over 4. And this will be 2 sine of 3 pi over 4, right? And cosine of 3 pi over 4 is negative root 2 over 2. And sine 3 pi over 4 is root 2 over 2. So this is negative root 2, and this is root 2. So the xy coordinates are negative root 2, comma, root 2. Is that clear? Easy, right? From polar to Cartesian is actually always very straightforward. The other way around, we just get one set of polar coordinates, right? We don't need to get all of them. We only need to get one. So this was part A. So let's do part B. Part B now asks to express the point with Cartesian coordinates as the point Q, 1, -1, from polar, I'm sorry, from rectangular, from Cartesian to polar. All right, so this is the X, 1, and the Y is -1. Okay, so then you get the R. How do you get the R? Well, the R is the square root of X squared plus Y squared. And tangent of theta is Y over X. So this will be 1 squared plus -1 squared. That's square root of 2. And this is going to be -1 over 1. That's -1, right? And then you ask yourself, what angle has a tangent of -1? So here, theta is, well, -1, that would be -pi/4. But it could be also depending on where the quadrant is, right? So that's what I was telling you here. Where is this point x1, x equals 1, y equals -1? Let's try to draw it, right? It's x comma 1, y -1. So it's in the fourth quadrant. So that's perfect. It's -pi/4. But if we had done x -1, so if we had switched it, well, I'll do it in a moment. Okay, so this one is good. So here, -pi/4 works. So the answer is √2 -pi/4. Now, if you don't like negative angles, just add 2 pi, right? You can add 2 pi. So if you add 2 pi to this, it will be 7 pi/4. So that's fine, all right? Now, let me just do the other one so that you could appreciate it. So here, the way we got -pi/4 is by doing inverse tangent. So this was actually arctangent of -1, and that's how we got -pi/4, okay? But now imagine that instead of being 1, -1, so let's call that C. So what about the point R, -1, 1? See, it's almost the same, right? Now X is -1 and Y is 1. When we do R, it's the same thing, almost. I mean, we just switch the order here. So it's still square root of 2. And the thing is, when we do tangent of theta, when we do Y over X, that's 1 over -1. So it's also -1, you see? But that's not the same point. So how can we note the difference? Well, here, inverse tangent doesn't work because this point, -1, 1, -1, 1 is in the second quadrant. So, right, this is the fourth over here. This is the second. If you are in the second quadrant, then arctangent doesn't work because arctangent only gives you between the fourth and the first, from -pi/2 to pi/2, right? -pi/2 to pi/2. And this angle is actually out of that. So to make it work, you need to add pi. So you can still use arctangent, but you have to add pi to the answer. So this will be -pi/4 plus pi. So that's 3 pi/4. And that's the correct angle, right? From here to here is 3 pi/4. So the answer is square root of 2, 3 pi/4. Okay, and that's what you need to do when you have things in the second or in the third quadrant. Okay, questions so far? All right. The next topic is to actually draw graphs in polar coordinates, right? So-called polar graphs. So what do we mean by this? Well, this time our graphs will be given by, so graphs are given by as r is a function of theta. So for a specific angle, I know what the radius is depending on the angle that you give me here. And we'll see some examples so that you see what kind of things we can do. The easiest ones are, for example, this one over here. Make my paper in a sec. So the first one I would like to see is when we simply make it a constant, right? That would be the easiest. So if we do, what would be the graph of r equals, say, 3? Right? Well, that's super easy, right? So for every angle, no matter what angle you give me, what I'm going to do is I'm going to have a radius of 3. So a radius of 3 means that I'm going to draw a circle of radius 3. And that's it. Very, very simple graph, right? R equals 3. That's the easiest of them all, right? Next easiest one would be this one. What if I make it R equals theta, right? How does that one look like? Let's try to draw it. So if I start at angle 0, the radius is 0. So at the beginning, I'm right here. And then as the radius starts to, as the angle starts growing, say from 0 to pi over 2, the radius grows as well, all the way to pi over 2, right? So it starts growing and growing and growing, and then at pi over 2, I'm right here, pi over 2. Then if I keep going, from pi over 2, it grows to pi, and then to 3 pi over 2, and then to 2 pi, and so on, right? So it's a graph that we could never ever describe with rectangular coordinates in an easy way because it's not the graph of a function, right? We get a spiral. Let me show you from the book. That's a better picture, I believe. So from the dynamic version of your book is what I mean. If you've never used that, maybe this will entice you to take a look at it. So it's available in your in my MATLAB. If you take a look at the so here it is the example of the one we just did, right? And you can move the slider to see how it starts drawing the actual graph, right? You can just add some values here, and you can see how you get the angle and the radius, right? It shows you the direction. So this is, for example, 5 pi over 6, and how big it is, 5 pi over 6, and so on, right? That's what happens as you move it along. It starts drawing this nice and beautiful ellipse. So they stopped it right here at 15, but it doesn't stop right here, right? It keeps going. So it's an infinite ellipse, not ellipse, sorry, spiral, right? It keeps going. Don't let this fool you into thinking that it doesn't continue, right? It keeps going and going and going. All right? Okay, so let me go to the next topic, which is how we can actually draw this, right? When things that are a bit more complicated. And we'll start with the following example. So it's example 4. Graph. Oh, the polar equation. R equals 1 plus sine theta, right? And I'm going to show you more or less what's the technique you can follow to do these things, how you can actually draw graphs like this, right? And notice it doesn't say theta from where to where, so we'll assume theta ranges over all possible values, okay? So here's how we do it. First, first draw this graph in the regular coordinate system, like, so we are gonna draw it like this. Say from 0 to 2 pi. What would be this graph? 1 plus sine theta, right? And we know sine theta goes like this, right? It's like a curve that goes up and down, but we're adding 1 unit to it, so we're moving it 1 unit up, right? So it usually starts at 0, so it's gonna start at 1, right? And it's gonna go like this. So when theta is 0, so we're drawing in a rectangular way where this is theta and this is r. That's what we're doing. Now this is gonna be an auxiliary graph, right? This is gonna help us do the real one. So this is an auxiliary graph. All right, so we start right here at 0, and at pi over 2 it goes all the way to 1. Then it's gonna come down, so it looks like this. Then over here, and then here, and then it repeats itself, right? It's periodic, like the sine function. So that's a graph you can all do, because this is something that we're used to, you know, sketching a graph like this is not that big of a deal if we do it this way. The complicated thing, the part that we haven't done yet, is how to do this now in the polar form, right? So let's give it a try. How would it work? Now, you can, of course, plot a bunch of points. That's always a good thing to try. So first you start right here. And what you want to do is you want to split this into little pieces that you can handle. Preferably from big points where things change, right? So here, what are the important points of this graph? Well, the beginning, this point where you get a maximum, this point where you get an inflection, a minimum, and then this over here, right? So pick those as your important points. In this case, they are pi over 2 and 3 pi over 2. And then break it down into those little pieces. So what's happening between 0 and pi over 2? Let's try to answer that question. So at 0, at angle 0, right here where it's horizontal, we start with a radius of 1. So my polar graph is going to start right here at 1. Yes? I'm going to start right here. And then what happens when I go from 0 to pi over 2? What happens when the radius, the angle grows from 0 to pi over 2? Well, the radius is going to grow, right? Good, Michael. The radius is going to go from 1 to 2. So it's going to increase, right? So this is now what you need to do on this graph over here. As you go from angle 0 to angle pi over 2, so from here to here, you want the graph to grow from 1 to 2 units. So let me mark it here. Here's 1 unit. Here's 2 units. So it's going to go from here to here. Now, how should I draw it, right? That's the next thing. How should I draw it? Can I draw it? Should I draw it, you know, like this? Let me give it the first try. Is it like this? So I go from 1 to 2. Well, let's analyze this. This way of drawing it, see, it starts at 1, and then this also looks almost like 1, and then 1, it doesn't, and then it's growing a little bit, but not a lot, right? Whereas over here, it seems like it's growing really, really quickly, right? We start at 1, and then it starts growing really quickly. So my graph is not good because it's not growing quickly, right? So it has to be a little bit more round, more fat on that side, right? So this is a wrong way to do it. It should actually open up. So grow, it starts at 1 and then starts growing. So it actually looks like this, in a fatter way, right? That's the point that I'm trying to make. Now, how fat you want to make it? Well, you can pick an intermediate point. For example, if you pick pi over 4, at pi over 4, sine of pi over 4 is radical 2 over 2. So this is 1 plus radical 2 over 2. And radical 2 over 2 is about 0.47. So at half the angle right here, this should be like 1.5, right? So that's how I know it has to be a little bit fat. See, maybe I went too far here because it looks a little bigger than 2. So more like this. All right, good. It doesn't need to be exact, right? I mean, we're learning how to do this. You can make it more exact if you plot more points. I mean, we could do pi over 3, we could do pi over 6, right? We can get a bunch of points and plot them, and it can presumably get better and better. I'll show you some pictures in just a moment from the book that are better, but I wanted it to do it without the book so you get an idea of how to do it by yourselves, right? Now, let's continue. Now, what happens from pi over 2 to pi? Well, now it's going to come down, right? So the radius goes from 2 to 1. And it does so in the same way as before. So you cannot revert what you did before. So why? Because this graph of sine looks the same from here to here as it does from here to here, right? So whatever we did here, we're gonna replicate on the other side from pi over 2 to pi. So as we go from angle pi over 2 to angle pi, we're gonna follow the symmetrical of the picture we just did here. So we're gonna go to 1 unit. So it goes like this, fat, fat, and then coming like this, right? It should be symmetric. Even if my picture doesn't look perfectly symmetric, it should. Now, let's see. Now what happens from pi to 3 pi over 2? So when we now go from here to here, from here to here, well, now the angle becomes, the radius becomes 0, right? As we go from pi to 3 pi over 2. So it becomes smaller and smaller and smaller till it reaches 0. How do we do that? Well, it becomes smaller. So from here to here, it's smaller, 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 smaller till it's 0. So it has to be something like this, right? Smaller, smaller till it reaches 0. And then from 3 pi over 2 to 2 pi, now it becomes bigger, bigger, bigger till it reaches 1, right? And so from here to here, bigger till it reaches 1. And in the same way, copying what we did before. So it goes like this, right? So it's kind of like an apple upside down, this graph over here, right? And it's actually has a name. It's called a cardioid. This shape that we just described, and it sort of resembles a little bit a heart, hence the name, cardioid. And I'll show you some better pictures from the book in a moment. Okay, so here's first a more detailed solution. If you plot more points, so you can see here on the screen, if you plot 0 and pi over 6, pi over 2, 5 pi over 6, etc., you can get this radii. And then with those, you can look at plotting those points, and it would make this shape, this cardioid shape, right? And then in the next one, it shows how we did it right now. So in here, as we move the slider, it will follow along on the graph of 1 plus sine theta, and at the same time, draw it in the polar form on the right side of this little graph, right? So as we go this way, move the slider, You can see it, right? So let me redo that part. So between 0 and pi over 2, it's growing, growing, growing. The radius is growing till it reaches 2. Then it comes down till it reaches 1. It's kind of slow for me. And then if we keep going, it reaches 0 and then grows again all the way to radius 1, right? So as you move on this sine curve, this tells you how the radius grow over here. Questions? All right, since I have this right here, let me see if I can make it actually go. Oh, over here. Okay, I'm gonna make it a little bigger, see if I can. Yeah. Okay, so since I have this electronic version of a book right here, I'll tell you about symmetry, right? We can tell some symmetries by the way a graph is. So if you have a graph where every time that you have r theta, r negative theta is also on the graph, think about that. So the angle theta is in there, r with theta, then r with negative theta is also there. So if you can change one angle by its negative, then that means the graph is symmetric with respect to the x-axis. If you can change r theta with r comma pi minus theta, or which is the same as negative r negative theta, then it will be symmetric with respect to the y-axis. If you can replace r with negative r, remember what we talked about, if you have the radius points in one direction, but if you make it negative r, it points in the opposite direction, that will make it symmetric with respect to the origin, right? I'll show you some pictures. I think that's the best one to explain it. So here are a few examples right here on the book. So this is the graph that you see over there. It's another type of cardioid actually, and it obviously is symmetric with respect to the x-axis, right? Whatever you see on the top, you also see on the bottom, and you can tell why, because every time you have a point, see how the point on the top or the point on the bottom, r comma theta. If you have r comma theta, if you replace it by r comma negative theta, if you flip the angle, you have the point on the top. So that's how you know this graph is symmetric with respect to the x-axis, right? Even for these small numbers. So r theta on the top, and then r negative theta on the bottom. Well, this is an example of symmetry with respect to the x-axis. Now here's one with respect to the y-axis. So this time r theta and r pi minus theta you can identify. And this is one where it's symmetric with respect to the origin. You can replace r theta with r theta plus pi, or negative r if you want, with the same angle in the opposite side, okay? All right, and this is important because sometimes when you want to graph something, instead of graphing the entire thing, you can simply graph half of it, okay? So let's try another example in which we graph something, and this time this will be example 6. And example 6 is about graphing graph r equals 3 sine 2 theta. Right, let me switch to the screen. All right, so we're gonna do this one. Graph equals r equals 3 sine to the 2 theta. And same as before, the way we're gonna do it is by first drawing this graph as theta on the x-axis, r on the y-axis, all right? So let's start with that. So how does this one look like? I'm gonna have a negative this time. Hold on a sec. It will look like Because of these three, this graph is going to oscillate from -3 to 3, right? So we'll go from -3 to 3. And this 2 theta makes it so that it oscillates faster, right? Twice as fast, as a matter of fact. So instead of being from 0 to 2, so we can do, so we're going to have the entire oscillation of sine between 0 and pi, and then the repetition of that from 0 to 2 pi. So pi over 2 here, this will be 3 pi over 2. And from here to here, we're going to have one oscillation of pi. And then the same thing again. Right? So that's our regular graph. If we go theta over here and r over here, regular rectangular graph. And this is the one we're going to use as our helping tool, right? Now let's see if we can now draw the Cartesian graph right here in this corner. So we'll start right here. And when the angle is 0, it starts at 0, right? So we start at the origin. And then let's analyze from 0 to, what is this angle? Pi over 4. So from 0 to pi over 4, what happens to our graph? Okay, so the radius grows all the way to 3 units, correct? So right here, it will be as big as 3 units. So where this distance is 3. And it will start from 0, grow, 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 and then reach 3. So something like this, right? That's our analysis from 0 to pi over 4. Now what happens from pi over 4 to pi over 2? So now from here to here, when we sweep from angle pi over 4 to angle pi over 2. Well, now it's going to come down, right? The radius is going to go from 3 to nothing, from 3 to 0 again. So, and in the same way as it went up, correct? So it's going to go like this. All right, so far so good. Now let's continue. What now from pi over 2 to 3 pi over 2? From here to here. So in other words, from here to, 3 pi over 4 is what I meant. From here to here. What happens then? Right? And this is what happens. The radius goes from 0 to -3. Right? So had it been from 0 to 3, the picture would be here. But because the radius is negative, it's going to go from 0 to -3. Then it has to go in the opposite region, right? So it's going to be, the graph will continue over here, in this part over here. Is that clear? Right? So because it's negative, it goes from 0 to -3. So I'm going to go from here. And instead of being in this region where it's the correct angle, right, from here to here, we're going to go in the opposite part from here to here. And what we're going to do is when we reach 3 pi over 4, the radius is -3. So it's going to end up right here at -3 when it's all said and done, right? So it's going to go like this. Yeah. Then from 3 pi over 4 to pi. So now from here to here, from here to here, from here to here. Again, the angle is negative. So it won't be in this region over here. It will be in the opposite one here. And now the radius goes from -3 to 0. So from here, it becomes 0. So it's going to go like this. Yes? Now, next. From pi to 5 pi over 4. So from here to here. Okay. No, so now it goes from 0 to 3. The same as it happened from here to here, right? So now I actually know what's going on, right? So from here to here in the same way. So it looks exactly the same like that, right? Then from 5 pi over 4 to 3 pi over 2. So from here to here. Now it goes back to 0. And then from 3 pi over 2 to 2 pi, well, again, it's going to be negative. So it's not going to be in this part over here. It's going to be in the opposite part. And I guess you can already tell that what we're going to get is these 4-petal rows, right? These 4-petal leaf rows, where all of these are supposed to be the same. They don't look like the same in my picture because I'm doing it by hand. But if you were to do it really, really carefully, each one of these petals should look exactly the same as every other one. All right, let me show it to you on our book. Have a better picture there. That's perfect. So here's how as we move along from 0 to 2 pi over here, it draws the corresponding one, the corresponding petal on the right side of the screen, right? The polar graph. Till it finishes the entire thing. And then after that, it repeats itself, by the way, right? I mean, I didn't make this specific when we did the cardioid, but if we keep going, say from 2 pi to 4 pi, well, it goes again through the 4 petals, right? And if we keep going from 4 pi to 6 pi, it again goes over the 4 petals and so on. So we don't need to keep track of all of that. It's just a matter of knowing that this specific graph redraws this 4-petal leaf over and over and over as in every period of 2 pi. All right? And this is an example of a graph that has all the symmetries we talked about, right? It's symmetric with respect to the x-axis, the y-axis, and the origin. And this can be verified. The book actually checks it. I don't want to spend too much time on that. But I wanted to show you other graphs in this last minute or so that you can see in your groups, in your book as well. So see, here's an instance of one that looks a bit more complicated. It is example 8. Is re to the sine theta minus 2 cosine of 4 theta. All right, that would be a difficult one to do by hand. But if you were given the graph on the left, you can sort of follow what's going to happen to the graph on the right. So let me just draw the entire thing, and I'll tell you. So you start right here at the point A, so somewhere over here at angle 0. Then it does this little loop, right? And let's see if we can. Yeah, so every time that your radius grows, like say this point D over here, where is this point D? Let's figure it out. Where is this point D? Well, this point D corresponds to this one over here, right? Where the radius is 1, and we went from this, doing this big loop. Then we repeat that big loop from D to E, and that would be that big loop over here. Then we come back to 0. That would be the point F. This point F would be right here in the center. Then we do a little mini loop in the negative side. That would be this one, little small one over here. Then we go high again, all the way to this point I. That would be one of these smaller leaves of this butterfly on this left side. And then again a mini loop. That would be the head of the butterfly. Then the other leaf, lower leaf of the butterfly would be this one over here. And then, and that's it, right? That's how you would obtain this one over here. If you can, just download the reader for this CDF file, and you can, at your leisure, scroll it and see how it's drawn, right? And here are some intermediate versions of how this. See, what I want you to realize is how flexible this system is. We can draw all kinds of graphs that we couldn't do before. So in that sense, it's fantastic. So graphing things in polar coordinates gives you an entire new type of flexibility that we didn't have before. Okay, so I'm going to stop now. We're already going a little bit over our time. What we're going to be doing tomorrow is talking about calculus in polar graphs, right? Specifically things like how can we calculate the slope of the tangent line? How can we get the area under one of these polar curves? Things like that, okay? So I'll see you guys tomorrow. Unless there are any questions right here, right now. Yes, go ahead, Saro. So the question is, from what chapter to what chapter is the test? And it will include the chapter 12. So sections, it's only the first 3 sections. And I think it's the entire chapter, let's see, I believe is all of chapter 11, right? So we did, I have to check, but I'll put it on our Canvas page. But my understanding is that we started with 11.1, so approximating with polynomials, so Taylor polynomials. And so it will be from 11.1 and chapter 12. So in a summary way, it's power series and this chapter 12, which consisted of parametric equations, polar equations, and calculus with polar equations, which is section 12.3. Remember that we have class on Thursday, right? Regular, well, actually, we'll review on Thursday. So I hope to finish the material tomorrow. And then we'll have Wednesday to finish up with the material if there's a little bit left, and then review. And then we'll also review on Thursday, right? And at the sometime on Thursday after class, I will make the exam public, and you will have 24 hours to do it. All right? Does that answer your question? Okay, great. You don't have a time limit. That's right. You have 24 hours to do your test. Well, 24 hours is the time limit. Harnit. Good. See you guys tomorrow.